Let us look at some numericals. Example 1 says, how many electrons per second constitutes a current of 1 milliampere in a conductor through any cross section. So, if we have a conductor of any cross section and if electrons are crossing through it, the question says, how many electrons per second will constitute a current of 1 milliampere. To understand this, let us recall the definition of electric current. And by definition, electric current is defined as the charge flowing by time taken. Here, time taken is equal to 1 second. So, if we put time as 1 second, then we get I is equal to Q. Mathematically I is equal to Q. Now here I is equal to 1 milliampere, which is 10 power minus 3, that is equal to capital Q, where capital Q is equal to the number of charge carriers into the charge value, which is N into E. So here it becomes N into E. There is no need to put a minus sign here because technically Q is equal to plus or minus N into E, but already the question says it is electrons. So we know what is N in this case, where N here is number of electrons. Therefore from here what we get is, we get N is equal to 10 power minus 3 by the electron charge, which is 1.6 into 10 power minus 19. So it becomes 10 power minus 3 plus 10 power plus 19 by 1 by 1.6. 1 by 1.6 is equal to 0.625. Therefore N is equal to 0.625 into 10 power plus 16, or N is equal to 6.25 into 10 power plus 15. This is a very high number. So if 6.25 into 10 power 15 electrons cross every second, then we get a current of 1 milliampere, which means a current of 1 ampere is a very high current, because for that we need even more number of electrons crossing a given cross section for every second. Example 2 says, find the current produced by an electron revolving round the nucleus in an orbit of radius r with a linear speed during one revolution. To understand this, we know that electrons will move in certain orbits around the nucleus. Let us assume for simplicity that these are like circular orbits in 2 dimensions. So if an electron moves in a given orbit, let the distance between the center to the orbit be called as r. So an electron will be moving around this with velocity called as v, which is tangential to this point. Velocity is v, and let its mass be m, and let the electron move around the orbit like this. So here we need to find what is the current produced. Now here, since a charge is moving, a current is produced. By definition, current produced is given by charge by time. Now here charge is charge of the electron, which is E, and time here is the time taken for one rotation. That becomes its time period. So only when the electron moves around the path once, we have a closed loop, then we get a current. So it becomes its capital T, which is its time period. But capital T itself is equal to distance by speed. So here distance covered for one rotation would be its circumference, which is 2 into pi into r, speed is v. So putting it back here, we get I is equal to E by 2 pi r by v. So v goes on top. Therefore current in this case is equal to EV by 2 into pi into r. So the motion of an electron will produce a current, and that current is given by this form. Example 3 says the charge flowing through a conductor depends on time as q is equal to 3t square plus 2t plus 1. Find the current produced in the first 2 seconds. Now here the charge flowing is not uniform, rather the charge entering or leaving a conductor is a function of time. So here q is equal to 3t square plus 2t plus 1. We learned that those cases where the charge is varying is called as variable current, and for that I was defined as dq by dt. In fact, this is the more general expression, the more correct. So when you put it back here, I is equal to, it is d by dt of 3t square plus 2t plus 1. If we break the terms one by one and differentiate this, then 3 comes out in the first term. It becomes d by dt of dt square for the first term, because constants comes out of the differentiation operator. It will be 2 here. It will be d by dt of t plus d by dt of 1, which is a constant, and differentiating a constant would mean it is equal to 0. That is equal to, it is here 3 into, this becomes 2t plus here it will be 2 into 1. So it becomes 6t plus 2. Now if you observe carefully here, even the current itself is a function of time. It is not a constant current. It is a current which depends on time. So the question says, find the current produced in the first 2 seconds. Which means when you put t is 0, the current what we get would be 2 ampere. It keeps on varying. So what we want here is, we want to find the current after 2 seconds. Which means I is equal to, it is 6 into 2 plus 2, that is equal to 14 ampere. So that is a required answer in this problem. Example 4 says the current produced by charge in a conductor is given by I is equal to 3t square plus 2t. Find the charge. So here what is given as I is given. So I is equal to 3t square plus 2t. We need to find what is the charge. Now we learned that I is equal to dq by dt. Now from here, if we need to find the charge, then charge is given by integral of I into dt. So we need to integrate this to find what is the charge. So here I is equal to integral of, q is equal to integral of, I here is 3t square plus 2t into dt. Again here we can break the terms. It becomes 3 comes out, that's a constant. So it is integral of 2 square into dt plus integral of 2 comes out, t into dt, that is equal to 3 into, this becomes 2 power t power 2 plus 1 by 2 plus 1 plus here it is 2 into t power 1 plus 1 by 1 plus 1 plus a constant of integration which is c. Now 2 plus 1 is 3. So this 3 and this gets cancelled, and also this 2 gets cancelled. Therefore what remains here is the charge is equal to t cube plus t square plus c. Now here this constant is not known to us. So what we can use here is, we can use some conditions. Here already a condition is given. So it says that at t is equal to 0, q is equal to 1 coulomb. So using those conditions, we can solve the problem. So even here, this charge depends on time. So question says, if time t is equal to 0, then the charge is given as 1 coulomb. When we put it back here, then what we get is we get 1 coulomb that is the charge when t is 0. So it becomes 0 plus 0 plus c. So this implies c is equal to 1. Now we know what is the constant of integration. So putting it back finally, we get q is equal to t cube plus t square plus 1. So this is the required form for charge.